Go ahead.
All right. Good afternoon, everyone. Welcome to Tech Talk on KMIT platform. Today's speaker is Dr. Haruko Wainwright. She's working as a research scientist at Berkeley National Lab, and she is also an adjunct professor in nuclear engineering at University of California, Berkeley. She has earned masters in nuclear engineering and stats and PhD in nuclear engineering at University of California, Berkeley. Her research focuses on environmental informatics with emphasis on stochastic hydrology and spatial statistics. She has worked on various topics in both nuclear engineering and environmental science, such as nuclear waste disposal, groundwater contamination, Fukushima radiation monitoring, and watershed sciences. So we are also at Applied Research Center under the cooperative agreement. We are working with her to support effort in ALTEMIS project. Welcome, Haruko, and the floor is yours. So please go ahead and present today's topic.
Thank you so much. Thank you so much for introduction, and it's wonderful to be here and giving this seminar. I have enjoyed working with some of FIU students, Himanshu, and others. So it's been a great opportunity for me to work with your university folks. And yeah, I hope to collaborate and increase collaboration in the future. So today I will talk about our project. This is the project funded by DOE EM. It's called Advanced Environmental Monitoring Systems Project, ALTEMIS, and we are aiming to develop the new paradigm of long-term monitoring at DOE EM sites and beyond. So many of us work on DOE EM sites. I assume that you know most of the sites, but I'd like to give you some overview of these sites, EM sites, DOE sites, just in case. And I would like to share my perspective as well. So Department Energy has been managing more than 100 sites across the US, which have been used mainly for nuclear weapon production during the World War II and during the Cold War. And Department Energy has been working on decommissioning of those facilities and remediation of environment for more than 30 years now. So just to give you sort of the overview of what we have, so the two big sites are the Hanford site and Savannah River site. These sites were used for reprocessing of nuclear fuel to extract plutonium. That's the primary material for nuclear weapons. Then there are many sites in the western US that had uranium mining and milling facilities. And Rocky Flat, you can see here, was like plutonium pit production. Other facilities, Paducah, Kentucky, Portsmouth, Ohio, are related to uranium enrichment. Oak Ridge National Laboratory, or K-12 facility, has had many different facilities, including reprocessing research. There was also a large lithium-6 enrichment facility that resulted in mercury contamination. The contamination at these sites are often associated with nuclear waste disposal. In 1950s or even 80s, low-level radioactive waste solutions were discharged in these kind of ponds or grounds. So here are the ponds, basins we call Savannah Riverside F area, or this is the area that in the Hanford site where the low-level solution were discharged, and this is the tailing pond at Rifle Site, Colorado. I actually have worked at these three sites over the last 15 years, I guess. What I usually say that these sites, it's a low-level radioactive waste solution, but I would say that, let's say the tritium concentration at F area was higher than, like 1,000 times higher than Fukushima groundwater right now, for example. And then also there are tanks at Hanford site and Savannah River site that stored high-level radioactive waste. They're still there, and some of the tanks at Hanford site are known to be leaking in the beta dome. So it sounds horrible in the current standard, but I would say that there have been mildly successful protecting the environment and public health. I would say that contaminant radionuclides stay mostly within the site, and the public health impacts are considered to be minimal or none. This is mainly because they are mostly located in remote regions. Well, they are selected to be secret, and therefore they have to be remote and far from the population centers. And that was, I think, good decision in terms of the environment and health perspectives as well. And I would note that there were significant planning activities involved in how to dispose those solutions. So I can show you one example. This is the map of the Hanford site. It is very large. It's 50 miles across the site. So it takes like an hour or so to get from one end to the other. The reactors are along the Columbia River because reactors generate a lot of heat. So reactors require a lot of cooling. But the reprocessing plants and most of the waste disposal sites are located at higher ground called Central Plateau, and it's very far from the river. The Central Plateau has very deep groundwater up to 100 meters, so that most of the contaminants are still stored in the beta zone, although there is some groundwater contamination detected. I have heard that the engineers at that time, even in 40s and 50s, were calculating the pore volume of this beta zone and how much waste that can be stored, or what is the amount of water actually evaporating to the air, so that waste or radionuclides get immobilized in this beta zone. Yeah, here is the first waste management. I have the first waste management document at the site, probably the first nuclear waste document in the world, and could be the first hazardous waste management document in the world as well. I would note that now people still fish in the Columbia River. I have seen people, I was there a year or two ago, there are people fishing at this site or doing sailing. And then surrounding this site, there are many vineyards and potato fields. So it has a thriving agriculture industry. And I think that these industries are there because there were significant planning activities during the 40s and 50s. I would say that this is a big stark contrast to other hazardous waste. In 50s and 60s, there were actually kind of health impact, like mercury, for example, or a bunch of sites in the US from polluted water across the world. And some contaminants like mercury, PCB are everywhere in the ocean. This is because hazardous waste in general were not legally recognized before 1976 in the US. So I could say that nuclear industries have been sort of ahead of other industries in terms of the waste disposal. Well, I don't mean to justify the contamination at the DOE sites, but I just want to give sort of larger perspective of sort of the contamination at EM sites compared to the contamination across the world. Nonetheless, these sites provide valuable insights about the environmental impacts of radionuclide contamination that could be useful for nuclear waste disposal from the commercial nuclear reactors, for example. So across the sites, for example, DOE actually has done pretty good studies to identify key and priority elements. Very interestingly, we tend to see similar nuclides across different sites. Hanford site is really dry, and now it's really hot. Like West Coast, including Berkeley, we don't get a lot of rain during the summer. It's really dry. Savannah River site, for example, is super wet. It has a lot of rain. But we see kind of very similar key elements: technetium, iodine, and uranium. Those tend to be very mobile elements. And then uranium is a primary contaminant in the western U.S. These uranium tailing mining sites. And there are also non-radioactive elements such as chromium at Llano, Los Alamos, and mercury at Oak Ridge. So I would say that it's kind of ironic, but people are very careful about high-level waste solution. They were storing those high-level waste solutions in the tanks and very careful treatment, which is really great. But ironically, low-level waste solutions are creating a lot of big plumes across the EM sites now. And those are mainly sort of mobile elements that are problem, like iodine, technetium. Those are very mobile. And we don't see, for example, plutonium or actinides as key elements, although, yes, they sound super scary, but they don't move in the environment at a significant distance or significant amount. And we shouldn't forget sort of the non-radioactive elements, mercury and chromium, for example. They tend to be a significant. They could have significant health concerns or risks. So coming back to the story of sort of history of EM sites, yes, there is 30-year history of remediation, and so they were successful remediating many sites. I would say the number of sites, number of active remediation sites has decreased from 100 plus sites to 16 sites, and there are these 16 sites are challenging, I would say. They tend to have large volume and low concentration plumes because it's too big to remove, but it's still higher than regulatory standards. And also some of the treatments like pump and treat are not so effective for low concentration plumes as well. And we can actually look at the broader perspective, broader sort of problem of soil ground contamination. There are so many sites across the US or in the world. Within the US, for example, there are more than 900 large contaminated sites we call Superfund sites designated by EPA, and more than 400,000 brownfield sites that has some kind of hazardous material in the soil or groundwater. And these sites have been under remediation for more than 30 years. Only, I think, like half of them have been cleaned up. So we can look at sort of the history of environmental remediation or cleanup. It actually pretty short history. The history is only like since 1990s or 1980s. So before the environmental laws were established in 1970s, people are just dumping and discharging all the hazardous waste because there were no regulations except for nuclear waste, I guess. Remediation started in 80s and 90s. First, remediation was very intensive treatments like soil removal and pump and treat. But now everyone is recognizing that they are transitioning from intensive treatments and sustainable methods, and I can show you why. So this is how actual remediation looks like at most of the sites. This is the picture that I took in Belgium 2 years ago. It is contaminated by uranium associated with fertilizer production. Phosphate rocks have a lot of uranium as phosphate rock, has a lot of uranium. So it's not nuclear site, but this is just a fertilizer site. But there is a significant uranium contamination. I saw that radiation level was higher than Fukushima, even, for example. So you can see that there are heavy machineries moving contaminated soil, but you might also recognize that they create a lot of air pollution, traffic, and also it produces a lot of CO2. And you can also see that ecological disturbance, and we have to think about what to do with soil, which is the waste. So, and another thing is sort of potential recontamination because of the soil disturbance, the soil could spread away. So you may think that this remediation can reduce the risk 100 years later, but it could increase the risk right now. So there is a trade-off. So there is a industry forum called Sustainable Remediation, and sustainable remediation consider not just contaminant concentration, but recognize these side effects of environmental remediation and think about how we can optimize the trade-off between contaminant removal, remediation versus these side effects like waste generation, CO2 emission, energy use, ecological impact, and also try to minimize the waste by recycling and reusing of the soil. And it promotes the use of in situ treatment or immobilization so that we don't create more waste associated with remediation. And it promotes the use of monitored natural attenuation. So basically, if it doesn't have the significant public health impact now and the future, it's okay to leave the contaminants at the site, in the place, in the subsurface, and as long as no one disturbs those soil. And this means that we have to control these sites, requires longer institutional control. So the key aspect is to establish alternative or attractive end use. For example, we don't have to use the subsurface, but we can put a lot of solar panels and generate energy. Or one of the EM sites, Rocky Flat, has been converted to natural wildlife refuge, for example. However, the challenge often is more sort of socioeconomic recovery. For example, I work on the Fukushima radiation monitoring, and there are a lot of fake news or negative news, although the cleanup has been progressing steadily. So people are still, people don't buy the agriculture product from Fukushima, and even though it is perfectly safe. So there is a lot of challenges in socioeconomic recovery, and this is not just Fukushima. It's pretty common across all the contaminated sites across the world. In terms of the perception, as you can imagine, the DOE sites have been challenging because it started as a secret, and until 80s and 90s, the government actually tried to hide these sites, or they didn't tell people what was going on in each site, right? So there was a significant distrust when the cleanup activity started. So that distrust is still hurting sort of the public perception and public acceptance of these sites or remedial options. I would say that DOE has been recognizing this challenge, has been and investing a lot of efforts on these communication and outreach. There is some encouraging news recently. So this is the news article about Rocky Flat I talked about. Now it's a national wildlife refuge. This article is saying that activists ignore the science says that Rocky Flat and so the science is saying that the Rocky Flat is safe. Basically, this news is supporting the government claim, which is, wow, it's very surprising. And if you read this article, they talk about monitoring data sets and how the data sets have been carefully archived and accumulated over the 10 years. And the monitoring data sets are saying that these sites are safe scientifically. So it's not just government, but I think that the science has a value to convince people that site is safe to use, at least as the surface, for example. So as an engineer, I think about how technologies can help this challenge of EM site, DOE EM sites. I think that long-term monitoring is really important for DOE EM sites. You saw the article. People believe in the actual data set, and it is really important for sustainable remediation, particularly because sustainable remediation often leaves residual contaminants. So we need to prove that the system is stable and there is no public health impact, or we can detect anomaly if it happens. And there are so many technologies now available, for example, different sensors and telecommunication technologies, so that we can establish in situ low-cost, low-maintenance monitoring. And we have many tools to do the model prediction of the contamination in the future, and we can have many approaches to do optimized monitoring. And I think it's really important to think at these DOE sites about public relation and public acceptance. And one thing is that we need to sort of empower concerned citizens and improve the transparency from the data sets, or even sort of the measurement to the analysis. This transparency will be important to tackle fake news, and we should make the data sets open and also the workflow of data analytics open, so that people can see and track themselves from the actual measurements to the conclusion, and they can actually think about themselves how safe it is for them, or they can evaluate themselves the risk and safety. So to achieve this goal, I am co-leading along with Carol Eddy-Direct at Savannah River National Laboratory the project called Advanced Long-Term Monitoring System Project. This is funded by Department of Energy, and the key is the integration of interdisciplinary research methods, including various sensing technologies, state-of-art sensing technologies, predicting modeling capabilities, and machine learning and AI. And we want to establish the new paradigm of long-term monitoring. Environmental monitoring is really exciting right now in earth science domain because there are so many new technologies. Like we have drones, here you can see we have many satellite images, and we have geophysics, subsurface imaging, and many sensors. So the key is to integrate different data sets, multi-type, multi-scale data sets that have different accuracy, coverage, and footprints. And also, we need to take advantage of proxy information. For example, there are sensors that provide a lot of proxy data sets, like electrical conductivity from geophysics, for example, can be a good proxy for contaminant concentration or soil properties. And then we need to take advantage of spatial and temporal correlation. And that's why machine learning and data analytics are very important. So I will show you some of the application results from here. So we are demonstrating our technologies at Savannah Riverside F area. We call it test bed of the technologies because we had many wells and many data sets, many historical data sets to test our approaches. So this site has this loadable radioactive waste solution disposal basin. And there are groundwater plume, including uranium, iodine, technetium, and tritium. And there have been several remediation approaches, including pump and treat. Currently, this site is using sustainable approach, in situ remediation approach, to immobilize uranium and iodine at this site. So we have been developing in situ real-time groundwater monitoring approach based on low-cost in situ sensors and wireless network and cloud computing. So we have identified that some of the in situ variables like pH or electrical conductivity are known to be a good proxies for contaminant concentrations, so that by measuring these properties real time, and we can see these measurement real time so that we can actually estimate contaminant concentration by establishing relationship through machine learning. So we can autonomously monitor this contaminant concentration, and we can detect anomaly if it occurs. And this is a really game-changing. Traditionally, groundwater sampling is done quarterly or even yearly, so we don't know if something goes wrong between this sampling. So if we have the real-time monitoring, we can detect right away. So we have established data analytics workflow. First, we do exploratory data analytics and analysis so that we can identify what are the in situ variables to estimate contaminant concentration. For example, we can see that specific conductance, electrical conductivity, basically, and also pH are very correlated with tritium concentration or uranium concentration at this site. And then we can actually quantify the correlation between, for example, specific conductance and uranium concentration. And we can, based on this correlation, we can estimate contaminant concentration. So we have established common filter approach. So we are measuring, let's say, a specific conductance and pH, and we assume that we have sparse uranium groundwater sampling data set, and we have the model to describe the evolution of contaminant concentration and relationship to these in situ variables. Then we can estimate contaminant, in this case, uranium concentration over time. So this is, we don't have the sensor yet. So actually this is demonstrating based on the historical data set. But here, red line, this red line is the estimated concentration, and blue dots are validation data set. So you can see that the validation data set is within a confidence interval. So we are, and also kind of capturing this, some of the dynamic spikes. So we are pretty confident that this approach is working. And this approach can reduce the number of uranium groundwater sampling, and we can also detect some anomalies and changes. So this we published this paper in 2018. It got a lot of attention, many articles published. So people are very interested in machine learning application or AI application in the groundwater monitoring or in environmental contamination, I would say. In parallel, we are pushing the boundary of prediction, plume prediction, contaminant transport modeling. So we are using new software called Amanzi, developed by the DOE as well. So this code is optimized for running on a supercomputer, and Amanzi itself solves flow and transport, Richards equation, and advection dispersion equation, and it's coupled with different geochemistry engine so that we can accommodate different level of sophistication in geochemical reactions. For example, Savannah Riverside F area, we have to have so many we have to take into account so many chemical reactions to describe uranium transport. We have many uranium aqueous species and surface complexation, and involving different metal and different cation as well. So these reactions are integrated into the predictive models, reactive transport models. Oops, sorry. So this is one of the, I don't know. Oh, yes. So here is the basin, and transport starts, and this is the plume going through the groundwater flow, and now it sort of hits the boundary. This is the river and going out to the surface, and you can see that there is a lot of contaminants left in the Beddoes zone, stuck in the Beddoes zone, and also there is a clay layer, so that a lot of contaminants, like particularly uranium, is stuck in the Beddoes zone and clay-rich zone. So based on this model results, for example, we evaluated the impact of climate change, what we should expect. Climate change impact is actually not trivial. So when there is a lot of water, let's say this is the idealized a diagram of the F area, but this is pretty common across different contaminant sites, across EM and beyond. So there is a lot of residual contaminants you saw in the prediction, but there it's in the Beddoes zone, there is a lot of residual contaminants, and there is a groundwater plume, and usually there is a surface cap or surface barrier. So when there is a lot of rain, extreme rain, right, we see recently, then it can mobilize contaminants, but at the same time, it can actually dilute the contaminants. So there is a trade-off between dilution and mobilization. In this paper, for example, we demonstrated that dilution and remobilization happen at different timing. So at first, when there is a lot of rain comes in, dilution happen, but we can, in the well concentration, we detect the remobilization effect 5 years or even 10 years later with the increased concentration. So in this study, we have found the importance of this surface capping. We have to maintain this surface barrier to limit the infiltration through the source zone, Beddoes zone. And also the source zone monitoring is very important to detect this remobilization effect. Another thing we are doing, our research focus is that characterization of this groundwater seepage zone. So in F area or many other contaminated sites, So the groundwater eventually comes up to the surface near the surface water or river. And so this is actually the primary sort of the contact location between humans and the contaminants. And then also the contaminants could go downstream to the river, to the population centers. But however, these wetland or groundwater seep zones often have a lot of clay-rich soil or organic-rich soil. We call it the last line of defense because this clay-rich soil can actually sequester and immobilize a lot of contaminants, particularly uranium and iodine. So this is great to have the last line of defense. At the same time, this is the vulnerability of the contaminated site because, or vulnerability if we think about long-term institutional control, because if there is a change in the water table or changes in the geochemistry, the sequestered contaminants could come back into the surface water. So this is the primary vulnerability location that long-term monitoring has to focus on. So in this project, we just started increased activities on geochemical characterization of the wetland soil and contaminants in the wetland. For example, iodine concentration is very dynamic, associated with rain and associated with precipitation and surface water. And we are establishing distributed sensor network in the wetland region to make sure this sequestered contaminant stay there for extended time. And this activity, I would say, is a really nice collaboration with FIU. Student Stephen Charles has been really terrific student, and also Angelique has been a really good mentor and great collaborator as well. And I would say that Hansel, sorry, I can't pronounce his last name, but Hansel is the FIU graduate and leading this geochemical characterization effort as well. At the same time, we are also pushing the boundary of radiation monitoring and mapping. Berkeley Lab has significant expertise on 3D radiation mapping, proven in Fukushima remediation activities. And in these technologies, we are merging different data sets, particularly lighter laser technologies and spectral gamma ray detection. We call it scene data fusion, so that we can actually map gamma ray sources and gamma ray radiation in 3D, and we can actually identify hotspots of this radiation gamma ray source, and we consider that's the hotspots of uranium at this site, for example. And lastly, I would spend time on the development of Python package for long-term environmental monitoring. This is called PyLenM, and it's been primarily developed under FIU Human Use team, and Aurelien, a graduate student in FIU, is the lead developer. So we are developing an open source Python package, which includes various functions to analyze groundwater contamination data set. This is open source and it's free and flexible, and it's very expandable in conjunction with many different Python packages that are available. And we hope to improve the transparency of the data analytics so that we can track from the raw measured data set to the data analytics, analysis, and visualization, so that anyone who is concerned about this site can look at this code or the Jupyter notebook and track the analysis step from the raw data set to the visualization. And we are not hiding the data set. We are 100% transparent. And hope that this will be helpful for sort of public relationship and also regulatory relationship. So I would say that PyLenM includes many sort of innovative visualization. So for example, this plot, you can see concentration as a function of year at different wells. So, and also you can see some wells started later than the others, and some wells could be discontinued. So we can sort of see where would be the good time window to do machine learning, and where would be a good spatial extent to apply machine learning. For example, we can map these wells. We can create interactive map online, and we can do QA/QC, sort of identifying outliers, and we can also do sort of extrapolation of the contaminant concentration, and we can find what would be the expected time to go below MCL at this site, which is important for planning at the contaminated sites. We have many sort of unsupervised learning methods. For example, we can quantify the correlation between in situ variables. I talked about specific conductance and pH, which can be measured by groundwater sensors, and they are correlated with uranium concentration. For example, specific conductance has a correlation coefficient of 0.9 with uranium concentration. We can also do clustering, so we can identify cluster of wells that have a similar behavior in terms of this covariate properties. And we are investing a lot of efforts to improve the interpretation of the contaminant concentration and groundwater elevation. For example, this is the groundwater elevation measured at different wells. Probably the Savannah River site or the Hanford site, those two sites could be that have the highest number of wells or density, highest well density at any contaminated sites, but you can still see sort of the gap between the wells. So we don't know the groundwater table between the wells. Oops, sorry. And then we know that ground surface elevation is a good proxy, and also topographic metrics like slope and topographic wetness index, for example, would be a good proxy for groundwater elevation. So then we can get this surface elevation from the Python package. Public data set is there are so many geospatial data layers that are publicly available right now. So we can use machine learning to merge these data set between the site-specific groundwater data set and publicly available spatial data layers. And then we can improve the groundwater table interpretation. So this function, for example, includes automated ingestion of publicly available DEM and process this DEM to calculate topographic metrics, and we can identify the trend or quantify the groundwater trend based on the different regression approach or machine learning approach like random forest, and we can interpret between the wells and create groundwater table map. And also we are developing we call model-informed spatial interpolation. So for example, this is the uranium concentration at the wells. As you can see, it's very sparse. And we have, you saw that reactive transport model. So we have actually model predicted map as well. So, but this is not perfect, I would say, but we can combine two information, model predicted map and actually measured concentration, and create a better map of better map of uranium concentration or uranium plume over the site. And we are working to improve this approach right now. Lastly, we have been developing well placement optimization. So at the Savannah River site, for example, we have too many wells, and we want to reduce the number of wells so that we can map the, let's say, groundwater elevation or contaminant concentration in a cost-effective manner. So my graduate student, Dajie-san, has developed the well optimization algorithm, and FIU team is now expanding and improving this well placement algorithm. And we can actually sort of select most important wells at this is the Savannah River site, and we can also observe that interpolation error goes up as a function of number of wells, but it sort of converges. So we can say that, okay, 14 to 20 wells would be enough to create accurate groundwater table map. The last aspect we are developing is that sort of more like across the different sites, what we can do the data analytics at different sites. I show 100 sites that DOE has been managing across the US. And for example, there is a concern about climate change impact, heavy precipitation or drying of the lowering the groundwater table. There could be or erosion due to heavy rain. So we want to sort of evaluate the impact of climate change across 100 sites. And traditionally, it's very labor-intensive approach. Probably either so many people work so many people have to work at each site in a coordinated manner. But now we have the power of sort of data analytics, and also sort of spatial data layers are well archived. For example, Google Earth Engine, we can get climate data set over the US daily at 1 kilometer resolution. So we can quantify, let's say, the temperature trend at the past 20 years at all the sites. What is the precipitation trend? What is the likelihood of heavy rain? Or what is the distance to the water body from each site based on topography information? So we can use this large-scale database and data analytics to do sort of the screening. Maybe before getting into particular site, we can do screening across all the sites and identify which one could be the most vulnerable site, and we can focus on these vulnerable sites. So this is a very sort of cost-effective approach based on the data analytics. And I think in the future, so this is not immediate, but let's say this is 5-10-year goal. But I think that AI and machine learning technologies will enable us to do more sort of the on-the-fly assessment. For example, we can find groundwater data set and topography data set at each site, so that we can develop a predictive model, contaminant transport model, and do the risk analysis. And we can do this in a more coordinated manner across all the sites and very quickly in a very efficient way. So here is some closing thought. I think that when we think about the future of the EM site, future of the DOE's legacy site, I think that Hanford site offers a pretty good, encouraging example. So this is the vineyard across the site. Here is the Hanford site. You can see some of the facilities here. As I mentioned, this region has thriving agriculture like vineyards, potatoes, and Hanford site now has been selected as the first site for the next generation nuclear reactors. So this is the good end use or good alternative use. And the most important thing, I think, is that, well, I think when we think about these vineyards, the most important thing is not the fact that this vineyard is across the Hanford site, but this vineyard is safe, it's not contaminated, and we can measure that and we can prove it scientifically. So I think that this is the sort of opportunity, or this is the need for monitoring. I think the technologies are there to do monitoring everywhere, all the time. So we just need to keep monitoring and prove that safety of this vineyard or other sites. Anyway, so this is the summary, and I know I'm running late, so I will leave this summary, and I'm happy to answer any questions. Thank you.
Thank you, Dr. Wainwright. I have posted some things on the chat just before we conclude. I know there might be some question. I don't want to take away from that. But don't forget, please, to fill the feedback form for this presentation. But I'd like to open the door at the time right now for questions. Anybody has any questions?
Go ahead.
So one question I think is from Aparna. In fact, she put that in the chat, asking, is there any hybrid model for AI/ML data-driven solution and combined with physics?
Yes, I have worked on surrogate modeling approach, or sort of physically enabled machine learning approach. This is the one of the direction that we are getting to. I'm aware that it is really important. I would say that to be successful, models have to be reasonably accurate, and making the model reasonably accurate is somewhat very hard for the contaminant transport model. So I think that hybrid models have been, many of them are around for groundwater level. Groundwater level prediction, groundwater flow prediction is relatively easy, I would say. So it's been there. I can give you many papers if you reach out to me. And yes, we are planning to implement that for the groundwater flow, groundwater table approach. Contaminant modeling is much harder, I would say. Let's say if you do that Bayesian approach, that ensemble of contaminant transport simulations have to include the actual contamination within that prior information. So I would say that's pretty difficult, but we have been developing this model for the last couple of years, and it's been getting better, I would say. So I think it's getting, I would say it's there. It will be there in 3 years, I would say, in this project, but it's hard, I would say.
Are there any other questions or comments?
So there is one question from Roger. He's also typing. I'm not sure why they are not speaking. Is computer vision being considered in any of the steps to assist the modeling or prediction?
I think there is a lot of opportunities. I agree. I work in the more climate science, and there is an application of computer vision to the simulation results, and simulation results are sort of within the environmental earth science prediction we do have sort of images, and we can have a lot of space complete pictures. I think yes, I would say yes, we are interested. Contaminant transport, in terms of contaminant transport, we can generate, let's say, 100 to 200 simulations. So that actually limits that type of regression approach that we can use. For example, we often see random forest is better than neural network because the sample size are still limited. But yes, we are interested using computer vision approach.
So Haruko, there's a follow-up question here. So one quick question on the ALTEMIS project. So we learned that there are a lot of sensors that are being deployed. Are there any sensors that are going to generate imagery data as compared to like sequential data or continuous data?
In terms of the image data set, this radiation mapping is probably the most comprehensive image, and this is the 3D. This is very similar to sort of self-driving car in terms of creating a 3D structure of the environment and overlaying radiation source intensity. So this would be a good one. And another one I didn't show here. We do have many geophysical technology. We have many geophysics technologies so that we can image subsurface electrical conductivity in general, like seismic or electrical methods. We call it electrical resistivity tomography. Those are sort of the images that can come out from advanced sensors.
All right. So do you have, thank you, Dr. Haruko. So do you guys have any other question, the participants?
Hey, can you guys hear me now?
Yes.
Yeah.
Oh, finally. Sorry about that. For some reason, my mic was giving me issues. I did notice, Haruko, that you said that, some of your data sets that were kind of limited, they were small. And you made the note that, decision trees at this point are outperforming neural networks. Have you guys considered augmented the data either synthetically or, using more samplings?
Well, maybe that simulation could be augmented data set to the actual concentration data set in terms of spatially. But yeah, the simulation data set, I mean, we can get to 200,000 simulations, but augmenting simulation data set, we can't do more simulations, or maybe we could do the surrogate models, but then that's sort of another regression approach. So yeah, we are thinking about it, I would say. Sorry, I don't have a good answer. I mean, it's been a challenge. I mean, groundwater flow, it's very cheap. We can do like 1,000 or like 10,000, but yeah, the simulation reactive transport, if we try to do it accurately, it is heavy, and this is sort of a big area of research right now. Not just contaminant transport, but climate hydrology simulations. We all share sort of the challenges, I'd say.
Got it. Thank you. The only reason I was asking is because a lot of times I deal with limited data sets, and we do spend a little bit of time trying to figure out how to augment it, get more samples in the best manner, possible, so that our models can be more accurate and more robust. So it's good that you guys are at least thinking about it.
Yeah, no, I think you might have more out-of-box ideas. I'll be interested. Thank you.
You're welcome.
Any other question? All right. So Thank you, Dr. Haruko, for excellent presentation. As you can see in chat, a lot of participants have really appreciated your talk, and it was very informative, especially with the ALTEMIS project and a little bit of history, like how this came about and what are the AI and machine learning and many different approaches that DOE is employing here and trying to solve these problems. So, so thank you for that. Thanks for your talk on this platform. We will be publishing, we are recording this, and we will be publishing this on the KMIT platform for the participants who could not attend today, so they can go and view this presentation as well. The other thing I wanted to announce was the next Tech Talk is going to be on 19th of October. And this talk will be from DOE fellow Roger Boza, who was asking a lot of questions here on image processing. He has done an excellent job in developing a solution focused on AI ML application to D&D problem set. And this talk will be focused on this area of research, which is being performed under cooperative agreement, which will be addressing the structural health monitoring of nuclear infrastructure using computer vision and image processing, where he has done the work using deep neural network, more focused on the convolutional neural network, as well as using YOLO, which is basically transfer learning. So all these will be the topics of this presentation, and we definitely invite all of you to attend this informative talk that will happen on 19th October. So, Walter, with that said, you have any closing remarks?
No, just a quick reminder that the slides for the presentation have been graciously provided by Dr. Haruko. They're on the website. Put the link on the chat. Please remember to fill out the feedback form and give some good information about what topics to look for next. And again, I want to thank you on behalf of FIU and DOE. I think we have. Do we have anybody from DOE still here? Thank you for your time, Dr. Haruko. Thank you for your presentation. It was well received and well informed, very informative, as Iman just said. Any final thoughts from anyone?
Thank you so much.
Yeah, just one more thing I wanted to add. Now we'll be shifting the time, changing the time from 1 p.m. to 2 p.m. So it will be 19th October at 2 p.m. So you just see that the invite will reflect that, and we just wanted to make sure that we may have more. We have more participants here, so we want to just get away from the lunch time. So it will be 2 p.m. on 19th October. A talk by DOE fellow Roger Boza.
Well, thank you, everyone. This concludes Tech Talk. Once again, thank you so much for the attendees. Thank you again, Dr. Haruko, and for presentation. Stay tuned for a future Tech Talk. If you want to be informed, there is also a sign-up sheet for a newsletter that you can sign up at the Tech Talk website. The link is provided again on the chat. Thank you again, everyone, and have a rest of a good afternoon.
Thank you.
Thank you
for having me here. Thank you.